This is group 10 with our final review meeting. This is our attendance list. Everyone is here. And then this is our design. As you can see, things are missing, but we'll add them later. For now, this is our algae book tank. We replaced it with a clear plastic bucket for the OD sensor. So these are our key innovations. We put the OD sensor underneath a clear plastic bucket so we could use the algae growing lamp as our light source. And that way we see through a lot of water. And we also added a siphon to remove a pump, more energy efficiency. And we also added a styrofoam box to help with the cooling. These are the parameters for our mathematical model. And as this is our graph. And as you can see, it stays stable over time for quite a while. And then some shortcomings of our model are that it doesn't take into account muscle waste or algae feeding, carrying capacity, or the effective temperature on the system.
For pump characterization, we had two different pumps. The small pump that took 5 volts. This had a stable flow rate of 60 milliliters per second. And the 12 volts one we could regulate in duty cycles. And you can see how we plotted that depending on the duty cycle.
So this is the PID controller. We tuned it and it was decent, but then we put in the styrofoam box, which made everything much more energy efficient. But this turns out that it makes it so the PID is way too aggressive. So it cooled it down to like 14 degrees. So not so good. We needed retuning. We retuned it and we got to a point where we were pretty happy. We stayed in a nice temperature range, but then we started having another issue, which is that in this nicely tuned version, we only pump very little water, and this allowed ice to form in the Peltier element to completely block it. Now I wanted to show a nice PID controller that works, but since we fried our ESP, we can't have that now, but it will be in the updated version. This is our OD sensor. It's one of our key innovations. We are looking through 20 centimeters of water since we're looking through the entire bucket. This means that we're able to see even very low concentrations.
So here we have a flowchart of the control code, which pretty much just shows that we send a temperature from our temperature sensor to the PID controller, which then sends a control signal to the cooling pump. From here, we have a data logger, which receives the current temperature, optical density, and the control signal. And if Wi-Fi is available, it will send the data to the Adafruit cloud. And if it is not available, it will log it to a local CSV file.
Now on to a bit more data management and electronics. We of course just talked about data management. We take some average temperature readings, and if we're online, we log those. If we're online, we send them to Adafruit. For the electronics, you can see a picture here, but we can also look at it in person. And for the web interface, we have 3 graphs, and then we have some sliders for which we can control the system in real time.
This slide covers the key biological parameters for our system. We calculated the muscle filtration rates using a Coulter counter, finding an optimal clearance rate of about 4.45 liters per hour per muscle at 1,130 cells per milliliter. Waste levels were too low to quantify with the NH3 and NH4 slabs provided. On the algae side, growth was dependent on light, nutrient, and temperature, with an optimal irradiance of 10 to 11 micromoles, photons per square meters per second, and a daily growth rate constant K of 0.382 for 24 hours, or over 24 hours.
Yeah, and for the thermal isolation, we tested the rate of cooling when the bucket had no insulation and when the bucket was in a styrofoam box. And we found that the rate of cooling was much, much higher when it was insulated. This brings us to the sustainability, where we can see that as the rate of cooling is much, much higher, we don't have to use so much energy when we have it in a styrofoam box. We also have a siphon, which removes the need for a pump, saving energy, and we switch off our Peltier controller when we're not using it.